Okay, so there's an amusement park ride of some sort of flying rat dog thing. Anyway, it's spinning at an angular velocity at zero point 0.8 radians per second. Uh, the R is following a sinusoidal path as described there, and Z is also following a cosine as given, right? So you start seeing R's and thetas and things of that nature, and you start recognizing, oh, hey, this is going to be polar coordinates. So that's what we're going to do. So we're going to draw our free body diagram. We're going to set it up based on the polar coordinates idea here. So uh, we'll start by drawing, we're just going to draw a dot instead of a rat dog flying thing. And the boy has well, I guess, yeah, I guess we're drawing the boy, not the rat dog thing. The seat, we're trying to find the forces of the seat on the boy. So the boy is 20 kilograms times 9.8 meters per second squared. So that means I'll have a force in the z direction, okay? I'll also have a force in the R direction, and again, that'll be out from the center, pushing on it, okay? And then perpendicular to that, there'll be a force in the theta direction. And again, we're setting this up based on polar coordinates because all of my equations are given in polar coordinates. So let's very quickly, maybe we'll do it right here. We'll set up our forces. So if I sum the forces in the R direction, it's just going to be uh, the whatever that reaction force R that the chair is putting on the boy times the mass of the boy times the acceleration in the R direction, which I'm going to go through and calculate here in a little bit. Same thing will happen in the theta or transverse direction. I'll have the force of the seat on the boy in the transverse direction times the mass of the boy times the acceleration in the transverse direction as shown there. Same thing with the z direction. The only difference is now I not only have the seat, but the uh, weight of the boy as well. So that's the negative 20 times 9.8, and that's going to equal the acceleration in the z direction, which will be 20 times az. So now what I need to do is I need to go through and I need to calculate ar, a theta, az, and that's going to be done using r dot, theta, theta dot, all that good stuff. So again, r is going to be given as 3 sine theta plus 5, okay? From that, I can learn that r dot is going to be, again, the 3 just pulls out in front, and again, I take the derivative of the inside with respect to time, so instead of, I bring out theta dot, and then the outside goes from sine to cosine. Okay, I go r double dot. Okay, now this time I'm going to have to do the product rule, right? So the 3 is constant, so it's going to show up both places. Take the derivative of the first, which will be theta double dot cosine theta minus 3 theta dot squared. So again, the idea is now I'm going to take theta dot times the derivative of cosine theta. So derivative of cosine theta, I bring inside out. That's where the theta dot comes out. That's why I have a second theta dot. So that's why it's theta dot squared. And then cosine goes to sine. That's why I have minus going from cosine to sine, like so. Okay. Now what I recognize is, again, theta is 120 degrees, which if I want to put in radians would be 2/3 pi radians. Okay. Theta dot, okay, that is given as the 0.8 radians per second. That's the angular velocity. That's how theta is changing. Okay. And it's constant, therefore theta double dot goes to 0. So what I can do is I can plug all of these values, all of, the 120 degrees, the theta dots, this one will actually go to 0 because theta double dot will go to 0. And I can find r dot, r double dot using that. So when I plug those values in, I get 7.598 for r. I get negative 1.2 for r dot. and I get negative 1.66 for r double dot. Okay, now I'll do the exact same thing in my z direction, and I'll set up, okay, well, z equals blah, 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 3 cosine theta. Z dot is just going to be the same idea where I pull theta dot outside, cosine goes to negative sine, right? So I'm going to get negative 3 theta dot sine theta, and then I go theta double dot, which will become negative 3 theta double dot sine theta minus 3 theta dot squared cosine theta, like so. Same idea, plug in my values, okay, and I get z equal to negative 1.5, plugging in 120 degrees, plugging in theta dot 0.8, blah, blah, blah. I get negative 2.08. And then here I get 0.96 for my z double dot. Now what I can do, okay, is I can then calculate, okay, all of my, well, I'll just do it right here. I can calculate, yeah, we'll do it this way. Running out of space here. AR, you'll remember, is r double dot minus r theta dot squared. Plugging in all the values that I've got there, I get negative 6.53. Do the same thing with a theta, and I get r theta double dot plus 2r dot theta dot. Plugging in all of my values that I get negative 1.92, and then az simply equals z double dot, which I just directly have 0.96. Okay, so taking those values, plugging those in to my force equations, I can find that Fr, okay, equals 20 times negative 6.53, which equals negative 130.5 newtons. F theta is 20 times negative 1.92, which equals negative 38.4 newtons. And then F in the z direction becomes, I'm sorry, that would be, why can't I do this better? That'll be 20 times 9.8 plus 20 times 0.96, which is going to equal 215.2 newtons. So these are the forces that the seat pushes on the buoy to get it to go around the axis as shown here. So again, set things up, recognizing that all of my equations are given in polar coordinates. I then set everything up in polar coordinates. You got to go through that whole process to find those accelerations. But once you do that, it then becomes a pretty easy problem to move forward with.